Hi everyone, and welcome to our first video on probability. So far, statistically speaking, we've discussed how to describe our data and how to display our data, but we haven't yet addressed how to draw conclusions from our data. You may remember way back when we talked about qualitative versus quantitative research, part of the difference is that quantitative research wants to be applied to people beyond the study. It needs to be generalizable. Probability is how that happens, so that's what we're going to be talking about this week. So, backing up a little bit, there are two main types of statistics, both of which we use in education research. The first is descriptive, and that's what we've already talked about. It is, as you already know, how we organize and summarize the data we have. Now, realistically speaking, everything we've talked about so far, all those descriptive statistics we've talked about, could be addressed by qualitative research. A survey, reimagined a little bit, but could become open-ended or done through interviews, and describing and displaying data is pretty similar to the idea of uncovering themes the way you do in qualitative work. But, like we said, for quantitative research, the real power is being able to make generalizations to a broader group. And in order to do that, we need to move beyond descriptive statistics, beyond just describing what our data says, and to start using inferential statistics. That's a much more complicated and powerful type of statistics. They're the ones that allow us to draw conclusions based on studies. When you hear or see in a study things like this was statistically significant or there were significant differences, that means that they've done inferential statistics and therefore can make inferences or generalizations about how the world works based on the study. And the reason inferential statistics are able to do that, the reason that they give us that ability to draw conclusions, is because they specifically link a population to a sample. So, first questions first, what are populations and samples, and why does that make inferential statistics so important? Well, the population is the set of individuals of interest in a particular study. So it's the group you want to generalize to. Let's say I'm doing a study on reading development in kindergarten. I want my findings to apply to pretty much all English-speaking kindergarten students. If I were doing a study on a particular ministry initiative, on the other hand, I might only want to generalize to English-speaking kindergartners in Ontario. The population isn't ever everyone, but it's the target group of individuals that you think could really benefit from this research. It's your group of interest. A sample, on the other hand, is the set of individuals selected from a population to actually be in a research study. There are actual participants. They're usually used to represent the population in a research study. So when I recruit 40 kindergartners in Thunder Bay to participate in a study, that's my sample, but I'm not really interested in their success. I'm interested in the success of all other English-speaking kindergartners in Ontario. So that's my population that I'm interested in. So the sample is really a small group that's selected to represent a population. Here's a little visual to help clarify that. The sample is a small group pulled from a larger group of interest. What inferential statistics do is draw a link between a sample and a population. They're the statistics that tell us whether the findings from our sample could realistically be applied. Another way of putting that might be, if you remember way back when we talked about philosophy, the idea was always that the interpretation and application of findings was built on quantitative research methods, which was built on positivistic philosophy. And then what post-positivism did is it went in and provided supports. This little section here would essentially be inferential statistics. It's the link between our methods, your study design, constructs, concepts, operationalizations, and what we can say they mean. And pretty much the rest of this course is going to be about understanding just this one little section of quantitative research. But in order to understand that one little section, we have to understand what it's built on. So we have to understand why, even if positivism doesn't really work, why the scientific method and probabilistic thinking still sort of does. Essentially, how does post-positivism buttress quantitative research methods in such a way that it gives us inferential statistics, which will be able to offer us interpretations of their findings in a context that applies to a population, not just a sample? And the answer to that question is probability. In order for inferential statistics to be able to link our findings on a sample to conclusions about a population, they have to be built on a foundation of mathematical relationships, and that foundation is called probability. When scientists started saying, we know this is likely true, instead of this is definitely true, and thus moved from positivism to post-positivism, it was probability that gave them the ability to do that, because probability made inferential statistics possible. And there's a two-step process by which we use probability in order to underlie our inferential statistics, which will link our samples to our populations. In the first step, we're going to use probability as a bridge from the population to the sample by identifying the types of samples that would be obtained from a specific population. In step 2, we're going to reverse that so that we can use the probability rules to say how its samples are going to tell us about populations. So it's essentially going both ways. In step 1, we make inferences about a sample based on what we know about a population, and in step 2, we use inferences about we make inferences about a population based on what we know of a sample. I know that sounds confusing, so let's do an example. Let's say you have 2 jars. You have 2 jars of marbles, and you're going to select a sample from each of them. And when I say sample, I mean you're going to pick one marble, that's your sample, from your population, that's the jar. So if one jar is made up of 72 blue marbles and 8 red marbles, and the other jar is made up of 40 red marbles and 40 blue marbles, you can figure out which jar you're most likely to get a red marble. That's step 1. If you draw a marble from the top jar, from the first jar, you know you're less likely to get a red marble from that jar. You're less likely to get a red sample from the population of the first jar. Whereas in the second jar, you're pretty much equally likely to get a sample of a red marble or a blue marble. But you can also reverse that. If you picked a marble without knowing which jar it was from, and you got a red one, you can make a solid inference that you got it from the second jar. That's because you know the second jar is more likely to get red ones. So if you have a red one, you're more likely to get it from the second jar. And broadly speaking, that's the goal of inferential statistics, making an educated guess based on the sample about what the population might be. So we start with a sample and then we answer questions about a population. But in order to be able to do that, we have to know the first part. We have to know how our population might help us make inferences about our sample. So that's why probability is important, because it gives us the power to make those inferential statistics. But what is probability? Well, it's big. It's huge. It's way bigger than we could hope to address in a single course, let alone a single week of a course. So we're just going to lightly touch on a few topics related to probability. Another big caveat to the rest of this is that all probabilities are based on this idea of random sampling, which means that each individual in a population has an equal chance of being selected, and if more than one individual is selected, there must be a constant probability for each and every selection. That's called sampling with replacement. And what both of these things mean is that, all things being equal, everyone in the population has an equal chance of being selected. That just means anyone could be in the study. Anyone could be a part of the sample. And then after each person is selected, they could theoretically be selected again. That's what the second part of this means. And that makes sure that the base rate doesn't change every time I draw a sample. So if I draw one marble and I don't put it back, my next draw, I would actually have, if I pull a marble out of the jar that has 7 marbles in it, or 8 marbles in it, 8 red marbles in it, and I draw a red marble and I don't put it back, then the next time I actually only have a 7 out of 79 chance of drawing a red marble. Okay, so I'm changing the probability because I'm not replacing it. So we always imagine that sampling happens with replacement. So as we draw a sample, we put it back and it has a chance to be selected again. So anyone that participates in our study has an equal chance of being selected again. Now, in reality, for education research, random sampling is basically impossible. For one thing, ethically, you can only sample people who want to be sampled. You can't make anyone participate in your research, let alone make them participate in it twice. So you can't say that your sample is random because it has to be based on a volunteer basis. You can't say, no, you have to participate in this. You have to have a chance of being drawn to this. That's not a thing that could ethically happen. And then for another thing, we're human beings and we're limited by a lot of boring things like time and money. I think the population for my research could be all English-speaking kindergartners, but I only have the resources to test kids in Thunder Bay. So this sort of pokes a big gaping hole in all the probabilities I'm about to talk to you about, and all the principles and all the mathematical theories I'm about to talk to you about, because it's going to sort of mess up our understanding of the probabilities. If our probabilities are flawed, isn't the entire thing flawed? And the answer is sort of. The math is going to be functionally the same, and it'll still be valid mathematically. The problem will be how we link our sample to our population, or the probability will still link our sample to our population, but our population might be different than what we think it is because we're not randomly sampling. So I'm going to talk more about this in video 2, but it's something to just keep in mind for now because I'm going to ignore it for the rest of this. So those big caveats out of the way, let's get down to talking about probability. And the good news is probability is something you've probably already encountered a lot. This is something we do every day. In fact, anytime we say, what are the chances, we're talking about probability. So let's start with an example. Take a minute now, hit pause or whatever, and answer this question. What is the probability of pulling a blue M&M out of this bag? I'm hoping now, just based on general knowledge, that you were able to see that the total number of M&Ms in my bag was 100, and that if 24 of them are blue, then that means that 24%, the probability of pulling a blue one would be 24%, 24 out of 100 or 24%. And that is basically all that probability is. It's the likelihood of any event occurring. And this is a sort of intimidating and somewhat overly technical definition for probability. It's called the analytic definition. And it's if an event can occur in A ways and fail to occur in B ways, and if all possible ways are equally likely, then the probability of its occurrence is A divided by A plus B, and the probability of its failing to occur is B over A plus B. Now that's mostly jargony nonsense. You don't have to worry about understanding that, and it's essentially what you already know, that the chances of drawing the blue M&M are the number of blue M&Ms divided by the total number of M&Ms. And I'm sure you guys have done this kind of probability 1,000 times since high school or since whenever, trying to figure out the chances that something might happen, the chances you'd win the lottery or win at gambling or any kind of that kind of gambling idea. Another way to define probability is called relative frequency. This is a slightly trickier definition to understand, but it boils down to basically the same idea. So if we keep pulling and replacing M&Ms 100 times, 1,000 times, 1,000,000 times, you'll find that the proportion of times you draw a blue one will work out to about 0.24, or 24% of the time you'll draw a blue one. And if it's easier, maybe think of it this way. When you decide to buy a car because of its high safety rating and consumer reports, what you're judging on is that a high proportion of these cars are trouble-free. That's essentially what consumer reports do. And anytime you do something in sort of a similar way, when you're basing it on people have done tests and overall it's very unlikely for this one thing to happen, or it's very likely for this other thing to happen, that's when you're using a relative frequency view of probability. Now, in terms of education research, these two definitions are distinct, but for us, the difference between them isn't really important. For hypothesis testing and education research, whatever definition you want to use, the interpretation of the results is going to be basically the same. Here are some more examples of probabilities. I really encourage you to take a minute now and work these out. Just put this on pause and work all these out. And note that you can present them as either a fraction, a 1 out of so many chances, or express them as proportions or percentages. For example, out of the whole deck, what are the proportion of kings? So in a lot of cases, working out the probability is really the same as working out a percentage. Now that kind of basic probability, I'm thinking everyone is probably okay with. It gets a little more complicated though when we start thinking about multiple factors and the probability of two things happening. In most cases, that's covered by the ideas of joint and conditional probability. Joint probability is the probability of the co-occurrence of two or more events. So the chances of being an education and a quantitative researcher, the chances of being a Star Wars fan and a Simpsons fan, basically the chances of any two things happening together. Conditional probability is the probability that one event will occur given that some other event has occurred. The probability of contracting AIDS given that you're an IV drug user. The chances of doing well in math class given that you believe in gender stereotypes. Essentially, the chance of one thing happening assuming another thing has already happened. So when we think about joint and conditional probability, when we're trying to work out what the joint probability or the conditional probability of something happening is, it's not like a formula where we work it out. It's about thinking about how probability works. So let's work through an example, which I think will make this easier. Let's look at parents and seatbelt use. Here we have a table that outlines the answers to a survey that had only 2 questions. Are you a parent, and do you wear a seatbelt? So let's start with the basics. If we took a random person from this group, what's the probability that we would get a parent? Well, we know there were 100 people total, and 20 of them were parents. So that means if we drew someone at random, we'd have a 20 out of 100, or a 20% chance of drawing a parent. So what about the other angle? What are the chances that a person sampled at random would be a seatbelt wearer? Well, it's the same deal. Total number of people who wear seatbelts over the total number of people. So if we drew someone at random, we'd have a 30% chance of drawing a seatbelt wearer. Okay, so now for the tricky bit. What are the chances that a person sampled at random would be both a parent and wear a seatbelt? I'm going to wait a minute and hopefully you yell it at the screen like a weird grown-up version of Dora the Explorer. Okay, hopefully in that time you guessed that, yeah, you'd be looking for the co-occurrence of those things and dividing that by the total. So the chances of sampling a person who is both a parent and wears a seatbelt is 15%. Okay then, so what are the chances that you'd wear a seatbelt given that you're a parent? Let's talk about the conditional probability now. I'm going to pause again and give you a chance to work that one out. Now hopefully here you figured out the little trick. When we're doing conditional probability, we're adjusting the base. That is, we're saying, given the people that are parents, what are the chances of drawing a seatbelt wearer? So we're limiting our group to only parents, and then we're drawing from that. We're limiting our population and drawing the sample from that and comparing them. So we're limiting so it's 15 out of 20, or 75% chance that you're a seatbelt wearer, given that you're a parent. So what this example shows is essentially joint probability is the chances of 2 things happening with all other things being equal. Conditional probability is the chance of one thing happening, but things aren't equal. You're limiting your population that you're drawing your sample from. So by changing the population, you change how you think about your sample. And that's essentially what conditional probability is. Okay, so that's basically how probability works with categories. And so far we've only been talking about categories. What are the chances that you're wearing a seatbelt or not? What are the chances that you roll a 6-sided die or not? Or a 6 on a die or not? But you can also look at probability for continuous variables. In fact, we already did a little bit of this when we talked about standard deviation. I mentioned in the discussions there that in any normal distribution, we'd expect 68% of people to fall within the first standard deviation. That means that if we have any variable along a standard normal distribution and we sample a single person, we can say that there's a 68% chance that that person scored within 1 standard deviation of the mean. And that's going to be true no matter what the actual mean and standard deviation are. And so that's really important because it means that for anything that's normally distributed, we can know the probability of a random person's score before we've even tested them. We know that there's a 68% chance that they'll be within 1 standard deviation and a 95% chance that they'll be within 2 standard deviations. And then we can also make this more precise. It's not part of the image here, but when we calculate the probability of being, but we could calculate the probability of being within half a standard deviation, or a 1/10 of a standard deviation, or a 1/1000th of a standard deviation, we can basically calculate the chances of being at any given point along this curve. And the way we can do that is by calculating something called a Z-score, which we're not going to talk about yet, but we will talk about, I think, next week. But that's essentially how you do it, and that's what you're doing. You're calculating the chances that a certain score would fall at any particular point along this curve. So far, we've talked about drawing one person, one sample from a population that is a single person. We've talked about drawing one marble, one person, placing one score, or the chances that one person would be in any given category. But most studies, of course, have more than one person in them. So how do we talk about probability when we're sampling more than once? And the answer here is actually a pretty straightforward extension of the probability definitions we've already talked about. For categorical variables, if there's a 24% chance of pulling a blue M&M from a bag, Then if we pulled 100 times, putting the candy back every time we draw, we'd expect our sample of 100 to have 24 blue ones. If we drew 50 M&Ms, we'd expect our sample of 50 to have about 12 blue ones, etc. Essentially, we expect the proportions in any category of the population to map onto the proportions in any category for a sample. For continuous variables, it works basically the same way. If 68% of the population falls within one standard deviation of the mean, then we'd expect 68% of the sample to fall within one standard deviation of the mean. And in fact, going even a little bit further, we'd expect the sample to have the sample mean and a standard deviation that have the same mean and standard deviation as the population. So if we had a population norm test like IQ, for example, in which the population mean is always 100 and the standard deviation is always 15, we'd expect that to be true for any sample. We'd expect that mean to be 100 and the standard deviation to be 15, and for 68% of the sample to fall between that mean and standard deviation. Now, of course, that expectation is a little bit bonkers. Probability works both ways after all. If there's a 68% chance that you draw one person that would be within the first standard deviation around the mean, that also means that there would be a 32% chance that there won't. And then the next draw, assuming replacement, is the same odds, then it's totally feasible for you to get a sample that actually ends up looking pretty different from the population. And that's called sampling error. And that's the discrepancy or amount of error between our sample stats and the population stats, or we call them population parameters, but it's fine to think of them as statistics. So if the mean of our population is 100 with a standard deviation of 15, and the mean of our sample is 90 with a standard deviation of 12, that's sampling error. Our sample just didn't turn out the way we expected it to. And then another factor with that is that the samples themselves are variable, in that they're not all going to be the same. So if we took two separate samples from the same population, those samples would be different from each other in addition to being different from the population. So if we took two samples, we might have one that has a mean of 90 and a standard deviation of 12, and then another that might have a mean of 110 and a standard deviation of 18. And that's going to be because each sample contains different people, which means different scores, which means different sample means. So if samples aren't always perfect, which they aren't, how are we then able to link them to the population? How can we generalize from a sample to a population if we can't say for sure that the sample is like the population? And the answer to that is, of course, drumroll, more probability. Yay! So here's where we start making that flip. Remember when we said there were two ways that probability helps us use inferential statistics? And the first way is that we can make predictions of our sample based on the population. That's what we've been talking about so far, the chances of getting a sample that looks a certain way. And this is where we flip it, where we can say, how can we make inferences about the population based on the sample? And that's what we're going to be talking about now. So the way we do that is we look at the distribution of sample means. And what that is the ability to predict sample characteristics is based on this idea that every possible sample for any population, there is a limited number of samples of any given size that you could get, or a different limited number of variations of types of samples you could get. And if we treat that, if we get the mean for every possible sample, and treat those means as scores, then we can create a distribution of all possible means, and we can make some inferences about that. So I know this is really where it starts to sound crazy. I know this is really where it heads into the tricky bit. But essentially, if we think about, instead of a population being individuals with individual scores, the population is every theoretically possible sample mean that could be drawn from that population. And then if we do that, we can use probability to say, what are the chances that we would get a particular sample mean? Okay, so I do realize how like banana pants crazy this whole idea sounds, and it is a really, really tricky thing to understand. So let's start with an example. Let's say we have a population that's only 4 people. There are 4 people in this population, and we are interested in only these 4 people. And they take a test, and there are 4 possible scores that each one of them gets. So let's create a distribution of sample means for a sample size of 2. That means we're going to take each theoretically possible sample of 2 from this population, and see what that distribution of means looks like. So for the sake of making this as random as possible, let's say that each sample is going to be a random sample with replacement. So what potential combinations could we get as we draw out samples? Well, on our first draw, we could get a 2, and then we put that 2 back, and on our second draw, we could get a 2 again. We could get that same 2 again, because it's with replacement, remember? Okay, or another possible sample could be that on our first draw, we get a 2, and on our second draw, we get a 4. That's also possible. Or we could do it where on the first draw, we got a 2, and then on the second draw, we got a 6. And that's 3 possible samples that we could get. Now what I want you guys to go do is go through and work out all possible samples that we could get. So work out all the different possible samples that we could get from this population based on one draw and the second draw with replacement. So it always goes back each time. Okay, so from there, we could go through and work out each possible mean for those samples. So mean here is going to be our main statistic for the sample, and we're going to treat means as though they were individual scores. So in our first sample, our first draw we got 2, our second draw we got 2. The mean of that sample would be 2. For the second sample we drew, our first draw was 2, and our second draw was 4, and the mean of that sample is going to be 3. So 2 and 3 there are our new data set. Those are our new individual scores. And so I want you to go through and for all the samples that you could draw up, so first draw this, second draw this, work out all the possible means that that could work up to. And then once you've done that, create a frequency table for those means. Remember a couple of weeks ago we worked on what frequency tables look like, and you did some in your labs. So let's go ahead and make those. Let's make us some frequency tables. And then from there, you can create a histogram. And from there, you can describe the shape, mean, and standard deviation of those means, which are now our individual scores, right? We're using those means as our scores. Okay, so go ahead and do that. Post it in the discussion forum that I've made for you guys, and then come back and watch part 2. Don't watch part 2 until you've already seen that. I really want to keep you guys to this, and we'll talk more about how you develop that. If you made any, mistakes, if you're finding this confusing, I'll be in the discussion sections to help you. But really, really, really go through and do this before you watch the second video.